So those last couple examples were involving an object that was rotating, but its motion wasn't uniform. Right? In both of these examples, we had an angular acceleration. So the angular velocity was changing, right? But we treated it just like, a regular kinematics problem. We were just using our rotational components instead of our linear components. So if you picture a point on the end of that wheel, right? Or if, let's say, you have like a mass on a string and you're spinning it around in the air in a circle. If you are spinning that object with a constant velocity, this is what we call uniform circular motion, right? So the angular velocity is constant. What also happens is every point on this object's path, this object has a velocity vector. It still has a linear velocity vector v. Right? If I take a snapshot of various points of this object's path, it behaves as if it's traveling linearly, right? Just for a split second, right? You've got a velocity vector at all these different points, right? So you have an angular velocity, but you also have a linear velocity, a translational velocity. Okay. Now, if I wanted to talk about this object's velocity as in terms of its displacement, the total distance that this object travels, let's say you're starting right here and you go all the way around the circle, the straight line distance that the object takes is the circumference of this circle. The circumference of this circle. So we go around one circumference, that's 2 pi r, and it takes a certain amount of time to get back to that position. And we call that time capital T. We call that the period. If you remember from experiments 2 through 4 in lab, then we have the time it takes for the pendulum to swing back and forth. That was a period. So this is an example of periodic motion too, because this object's going to go all the way around and it's going to come back to its same position, and then it's going to repeat, and it's going to do it over and over and over again. So this is a form of periodic motion, and so we call the time it takes this object to go around a circle one full time the period. So this is in r would be in meters because it's a length, t is in seconds. So we're in units of meters per second. This is one expression of our translational velocity, or our linear velocity of an object that's exhibiting circular motion. Sometimes we call it tangential velocity. We call it tangential velocity because this velocity vector is always tangent to the circular path. Excuse me. So this velocity vector is always tangential to the path. Now here's the issue. We call it uniform circular motion. That's great. The velocity is constant, right? Angular velocity is constant, velocity is constant. You're spinning something around in a circle at a constant rate. That's fine. But the definition of acceleration is change in velocity with respect to time. Acceleration is a vector, so is velocity. So while the magnitude of this velocity vector is constant, right? The speed's the same. It's changing direction. Okay, it's changing direction. So if you're going around a curve, if you're steering your car around a turn, even though you're on cruise control, you're still accelerating because your velocity vector is changing direction. So any change in a velocity vector results in an acceleration. And so we're going to call this v tangential. Right? Your tangential velocity is this vector v. And it's always changing direction as you go around the circle. So here's our relationship between tangential velocity and angular velocity. Right? So you do have an angular velocity as you're going around the circle, but you also have a tangential velocity at different points. How do we get this expression? So I start out with the definition of arc length from the first slide, and then our definition of angular velocity. So basically I'm looking at how theta changes with respect to time. So I'm going to take my arc length expression, and anybody who took calculus, I can take the derivative of both sides of this, right? I'm not actually taking the derivative, I'm just multiplying both sides by delta over delta t, right? So I'm seeing how these two, the two sides of this equation change with respect to time. So I'm kind of, don't tell your math teacher this, but I'm kind of multiplying, and I'm using finger quotes right now, I'm multiplying both sides by delta over delta t. All right, not a rigorous mathematical operation, but so delta S over delta T is actually the change in the arc length over time, right? So the change in the arc length is actually one full circumference, and the time it takes to get all the way around that circle is the period. So this delta S over delta T is the same as this right here. All right, so that's my tangential velocity. And over here, the radius is constant, so it's not going to be changing with respect to time. So I factor that out, and the only thing that's changing is theta. So now I have a delta theta over delta t. But delta theta over delta t is my definition of angular velocity. So this becomes omega, this becomes v tangential, my tangential velocity. Right? Both sides of these are still meters per second. Right? This is meters per second. This is meters radians per second. And, you know, per the last video, we kind of ignore radians. It's like a pseudo unit type of thing. So we started out just kind of using it as a placeholder. So these these two sides of the equation, they have the same units. So if I have an angular velocity, I multiply it by the radius, I've got the tangential velocity. If I have the tangential velocity divided by the radius, I've got the angular velocity. So that's my relationship between my linear and my rotational components. And a couple other things that would be helpful, on occasion you might be asked for a couple other things. I'm going to set omega r times 2 pi r equal to 2 pi r over t. So I'm taking this expression, which is equal to v, and I'm setting it equal to this. The r's go away, so I have a relationship between the angular velocity and the period of an object traveling in a circle. So omega is 2 pi over t, also t is 2 pi over omega. Right, so maybe if you're asked for the period and you're given the angular velocity, this is a quick way. You don't have to convert it to linear velocity and then substitute it back in here or anything like that. Right, so this is my relationship between the period and the angular velocity. Sometimes you'll see omega is referred to as angular frequency. Sometimes you'll see it as angular frequency because this is periodic motion, right? It does repeat itself. It's often useful to talk about its behavior in terms of frequency. So there's angular frequency, and then there's just straight frequency. If you remember, like the electromagnetic spectrum from chemistry class, right? You see like the relationship between wavelength and frequency, right? So you saw frequency a little bit as far as like how waves behave. So frequency is cycles per second. That's how many times this object will go around in 1 second, right? So angular frequency is basically our angular velocity in radians per second. This is our linear frequency in cycles per second, 1 over seconds. We also refer to it as hertz, okay, named after Heinrich Hertz. So that would be a capital H, lowercase z. But we'll stick with 1 over seconds just so they, just so they agree with our units already. So if the frequency is cycles per second, then it's the inverse of period, right? It's the inverse of the period of the object's motion. The inverse of the period is omega over 2 pi, right? See this right here? So omega over 2 pi is equal to f. So that means the angular frequency is the frequency times 2 pi. That's how we get our radians back in our units, right? So if you're ever given the frequency, you can convert it to angular frequency just by multiplying it by 2 pi. Similarly, if you have the angular frequency or angular velocity, you divide it by 2 pi, you get the frequency. So on occasion you might be asked to find the frequency in hertz or inverse seconds or something like that. So given the angular frequency or even the tangential velocity or the period or anything, you can see the relationship amongst these variables and solve for f if you have to. So that's frequency. So basically what's happening here is you have, like I said before, you have a constant tangential velocity. Its magnitude is constant, right? You're going around the circle at a constant rate, constant angular velocity. But your velocity vector is changing. So I want to know what the direction of the velocity vector's change is, right? Basically, the direction that delta v is pointing in is the direction of your acceleration. So what I did was I just took a portion of that circle and I drew two velocity vectors. I've got a v final up here, right? I drew it as tangentially as I could to the best of my ability there. I've got v final tangential to the circle right here, and I've got a v initial. So what I did was I took these two vectors, I didn't change their direction or their length, and I moved them over here. So here's v final. I took v initial and I flipped it around, right? I flipped its direction. I made it negative v final. And so I'm adding these two vectors graphically. So I'm adding v final plus a negative v initial. So v final minus v initial is this vector right here, right? I'm using the tip to tail method from chapter 3. V final minus v initial is this, delta v. Now if I took this vector and I put it back here on the circle, it would be pointing towards the center, right? I could do that for any group of velocity vectors that are tangential to a circle, and I'll always get a delta v that's pointing towards the center of the circle. All right. So that's what we call centripetal acceleration. Centripetal acceleration. This acceleration keeps the object on the circular path, right? If you were spinning that object around on a string and you cut that string right here, if you cut the string right here, that object would just go in a straight line. There's nothing keeping it on that circular path anymore, so it would just follow Newton's first law. It would be in motion in this direction. It would stay in motion in this direction because there wouldn't be any force acting on it. Okay? So that's my centripetal acceleration. Even though I have a constant angular velocity, I don't have an angular acceleration, but I have an acceleration towards the center of the circle. Okay? And so that's centripetal acceleration. I don't talk about centrifugal acceleration. That's kind of a fake force. It's just an experience that we have when we're rotating. So we just refer to the acceleration of an object that's rotating as centripetal. Okay, center seeking. All right, all you Latin scholars out there, you can find the root word for seek in there. Center seeking acceleration. Okay. And so what I did, I'm foregoing the definition here, or the derivation of this acceleration. You can find it in your book. It's at the beginning of chapter 7, shortly after they do rotational kinematics. But this is my relationship between my tangential velocity and my centripetal acceleration. So centripetal acceleration is v squared over r. I can also write this in terms of angular velocity. If I substitute omega r in for v, square both of those terms, 1r goes away, my centripetal acceleration can also be found by omega squared times r. So these are very useful equations right here. V squared over r and omega squared r. Okay. So any object that is following a circular path, it may not have an angular acceleration alpha, but it will always have a centripetal acceleration. All right, an acceleration towards the center of the circle, which causes its velocity vector to continue to change direction and keep it on that circular path. Now, how do I accelerate? I have to accelerate when a force is acting on me, right? If there's a net force acting on an object, there's a net, or there's an acceleration on that object. So any object that's on a circular path is experiencing what I refer to as a centripetal force, right? So what was keeping you on this circular path here? What was keeping the object on this path? It was that string. So it was a tension in the string that was keeping it on a circular path. Right here, this race car driver is on a circular path, and the car is on a curved path. It's on a banked curve, right? And it's actually the normal force, and we'll do a problem like this later. It's actually the normal force and the friction that's keeping this car on the circular path. Okay, so centripetal force, right? I think I'll refer to it as F sub c, right? F sub c. It's not its own unique force. It's not some special force out there in the universe that we discovered. It's due to a force that we've already mentioned, right? You've got friction, you've got tension, you've got a normal force, you've got an applied force, something like that. A centripetal force is actually the result of forces that we've already discussed keeping it on its circular path. Okay, so basically this is F net in the centripetal direction, right? And I'll define what I mean by centripetal direction later. I'll do a couple examples. Okay, so this is Newton's second law for circular motion. F net is ma sub c, right, which is mv squared over r. mv squared over r. So let's do a flat curve. All right, we'll do a flat curve first. Sometimes it'll be referred to as level or unbanked, right? So if you either see the word unbanked or level or flat, you'll know it's a flat curve. All right. So what happens is we've got a 1,500 kilogram car driving around a flat curve. Now the radius of that curve is 50 meters. Now the coefficient of friction between the rubber of the tires and the road is 0.1. So we've got a coefficient of friction between the tires and the road. We've got a radius of this circular path, and we've got the mass of the car. So we want to know how fast this car can negotiate the curve without sliding. So what's happening, right? How are we allowed to even go around curves on the road? Because when you hit a curve, you have a velocity in this direction. But you turn the tires, right? When you turn the tires, the frictional force between your tires and the road actually points towards the center of the circle. It's perpendicular to the direction of your tires, right? So that frictional force is pointing towards the center, and so this frictional force is what is contributing to your net centripetal force. And so you have an acceleration towards the center of the circle, which causes you to go around in a circle. Now what we're looking for is we're looking for this limiting condition, right? You could go too fast. You could hit a curve too fast, and your speed could actually overcome the friction between your tires and the road, and you would actually maintain this speed, right? You'd maintain this direction, right? Your tires wouldn't grip and you wouldn't go around the circle. So this is actually how engineers create roads, right? Whether they have to bank them, whether they have to keep them flat, what their radius has to be, right? And then if you see those little caution signs, like those little warning signs, they're like yellow diamonds, and it says, 40 miles an hour. That's the speed that they recommend you to have to safely negotiate a turn, right? Because they took all of this into account. Right, so they're telling you, like, don't go too fast around this curve or you're going to slide. So what I do here is I draw a free body diagram, but I don't draw a free body diagram from looking at the top of the car, looking at the side. So basically you want to picture yourself standing behind the car as it's going around the circle. So we've got two directions now. We still use two dimensions, but we've got the z direction, right? Because technically the plane, right, the surface that you're on is the xy plane, and so they call this the z direction. What I'll do is I'll ignore that it's the z direction, and I'll just call it the y direction, because it's basically the same behavior or similar behavior in this direction for most of these problems. Okay. We've got the z direction, again I'll call it the y direction. So we've got this dimension, and then we've got the axis towards the center of the circle, which I'll call the R direction. And I'll call the R direction. So I'm standing behind the car. My free body diagram looks like this. I've got the normal force from the road. I've got the force of gravity. Right? This is very familiar, right? Just like a block sliding across a floor or something like that, right? We've got normal in the positive z, gravity in the negative z, and then we've got the force of friction towards the center of the circle. Okay, so here's my free body diagram. So I want Newton's second law in both directions. Right? I want Newton's second law in the z direction and the r direction. I'll zoom in a little bit here. Okay. So Newton's second law in the z direction is the normal force minus the gravitational force, which is equal to 0. Right? There's no acceleration. You're not leaving the surface of the road. So the net force in the z direction is 0. The net force in the r direction is the frictional force. The frictional force. Now this is a lowercase s. I've gotten some questions about the s and the k before. This is rolling friction. Okay, this is technically rolling friction. So what happens is your tire rotates, but the surface that's in, or the part of the tire that's in contact with the road is actually rolling across the road. Okay, so it's not slipping, it's not sliding like when we were sliding a crate across a floor. That was kinetic friction. Right? So that crate was sliding across the surface. This is rolling friction, so we refer to it as a form of static friction. We actually don't want kinetic friction between the tires and the road, because that means you are slipping and your tires aren't gripping the road. So this is my frictional force. Notice there is no F sub c here, right? Centripetal force is not its own unique force. It's due to some force we've already talked about. And in this case, it's the friction that's keeping you on the circular path. So it's pointing in the r direction. So the frictional force is equal to the mass times the centripetal acceleration, v squared over r. Right? So we're looking for max speed, right? We're looking for max speed. So we can solve this Newton's second law equation for v. And we get this right here. Right? So it's the square root of r times the frictional force divided by the mass. What's the frictional force? It's not in here, right? Also, by the way, the picture that I used here has a little typo here. The coefficient of friction is 0.1. All right, so I have 0.1 in the solutions. It's just a little mistake there on the picture. So I've got an expression for the velocity, but I need to find the frictional force. Okay. So what I do is I actually solve for the normal force, right? The normal force is equal to gravity, mg, and then I solve for the frictional force. The frictional force is mu times the normal force, and the normal force is equal to mass times gravity, so mu mg is the frictional force. Okay, so mu mg equals mv squared over r. Right, so the frictional force, mu times the normal, mu mg, is equal to mv squared over r. The masses go away, and I have v squared over r equals mu times g. So now I can solve for v, multiply both sides by r, take the square root of both sides, and have v is equal to the square root of mu gr. So what this means is basically it doesn't matter how massive your car is. It doesn't matter how massive your car is. It depends on the coefficient of friction, the acceleration due to gravity, which is a constant, and the radius of the curve. So notice, if the coefficient of friction is higher, I can go around the curve faster. If the radius is larger, I can go around the curve faster. Right? That kind of makes sense, right? My tires will grip the road better with a higher coefficient of friction, and the larger the radius, the smoother the curve, right? It's not as sharp of a curve, and so I can travel around it faster. Plug my values in here, 0.1 for the coefficient of friction, 9.8 meters per second squared for gravity. The radius of the curve is 50 meters, and I get 7 meters per second. Okay, so that's the maximum speed you can safely negotiate that curve without slipping. So for a level, unbanked curve, this is my free body diagram, and these are my Newton's second law equations that I use to find max velocity. So basically, another thing that we could do is we could have a radius and have a velocity, and we can look for the minimum coefficient of friction, right? Maybe they want to make the road out of something to where there's higher grip, right? So people can negotiate that turn, right? Maybe something like on a highway where you've got a turn in the highway, but people are going, 65, 70 miles an hour, something like that. So I've got a radius of 80 meters, and the car is traveling at 25 meters per second. So we need to know what the minimum coefficient of friction has to be so that car can safely travel at this speed around the turn. So it's nearly identical, right? It's the same type of problem, same free body diagram. Newton's second law in the y direction and the r direction are both the same, okay? So I still have the same relationship, right? V squared over r equals mu times g. I do the same algebra, but instead of solving for v here, like I did in the first level curve problem, I'm solving this for mu. So all I have to do is divide both sides by g. I'm looking for a minimum coefficient of friction. So I've got the velocity that the car is traveling, I've got the radius of the curve, I've got g, and I get a coefficient of friction of 0.8. So it's a very high coefficient of friction because 25 meters per second is a very high rate of speed, and this curve, it seems like an 80 meter radius would be a lot, right? But this car is going pretty fast to negotiate that curve. So we would need a very high coefficient of friction for that car to safely go around that curve at that speed. Okay. And then if we have ice or rain or something like that, right, that coefficient of friction goes down. That's why we got to slow down when we're driving on roads like that, right? The coefficient of friction would be much lower. This car would definitely slip if it was going around that curve. Okay. So again, same free body diagram, same Newton's second law. We're just solving for something different, right? So try another one. Solve for r, right? Make up a velocity, right? Say I'm going around a curve at 20 miles an hour, convert it to meters per second, use Google, whatever. Give it a reasonable coefficient of friction. Find out what the radius of that curve has to be. Okay? So that's basically what we're going to do. V, mu, and r. These are my variables that are going to be asked for in a level curve problem. So we go to we'll go back to our race car. All right. Not all of our roads are flat, right? Some turns you'll notice that they're banked, right? When you go into a turn, you'll kind of feel the car tilting a little bit. That's because they banked the curve. And the reason they banked the curve is they want another force to contribute to your centripetal acceleration. Right? When you bank the curve, your normal force is not strictly pointing in the z direction anymore. Right? Your normal curve is not, or your normal force is not pointing straight in the z direction. It's now pointing in this quadrant right here. Right? It's pointing in the z direction and the r direction. Okay, so now there's a portion of the normal force that's pointing towards the center of the circle, which is helping your centripetal acceleration, which is helping you accelerate towards the center of the circle. Gravity is still in the negative z direction. All right. Now I'm going to take the simple case here where there's no friction. All right. Simple case where there's no friction. So it's, in this case, it's just the normal force that's going to be contributing to the acceleration, because in this sport here, right, this stock car racing, the track is asphalt, but the tires are much slicker, right? They're much slicker for purposes of traction, actually slowing the cars down, right? If you ever see like a NASCAR car's tire, it's a lot smoother, right? It doesn't have tread like ours. So they have to rely on their normal force to keep them on the path and keep them from sliding up the track and running into the wall, right? So they have very slick tires, but it's the normal force that's keeping them on that path. Okay. So in this case, we'll just neglect friction. We'll say the friction is low enough that it's negligible. So our free body diagram now looks like this. We've got the normal force, right? Here's my banked curve. We've got the normal force, and we've got gravity. Now, when you were on an incline before, when we had a box or a skier going up or down an incline, sliding up or down the incline, we split the gravity vector up because it matched the motion, right? There was motion parallel to the surface. So we split the gravity up and left the normal force alone, and we changed our coordinate system and everything was good. Now it's different because this car isn't moving up and down the track like this. It's going around in a circle. This is still our rear view. But gravity agrees with our coordinate system. So gravity is now pointing in the negative z direction like it was before. So we don't want to mess with that. What we want to do is we want to split our normal force up into the z direction. Again, I'm calling it the y direction. It doesn't really matter. Not to intentionally confuse you or anything. This is just the motion vertical, right, perpendicular to the circular path. This is motion in the circular direction, or in the radial direction. So I'm going to split the normal force up instead of gravity now. So this angle right here is this angle right here. Right? So this is the angle of incline when they bank a curve. That's the angle that they're referring to. This angle is also this angle right here. So this normal force vector is the hypotenuse of a right triangle. Okay? So this is the normal force in the y direction or the z direction. This is the normal force in the r direction. So I've got a y component, I've got an r component. Again, it's kind of backwards like the gravity one was, right, with the inclined plane. But the normal force in the y direction, right, see this is the adjacent side of my angle now. The normal force in the y direction is the normal force times the cosine of theta. And the normal force in the r direction is the normal force times sine theta. Okay, so again, they're a little backwards, right? But just practice resolving that normal force into its y and r components for this type of problem. Now I want to set up Newton's second law in the y direction, right? The vertical Newton's second law. So it's not just the normal force is equal to the gravitational force. The y component of the normal force is equal to the gravitational force. So that means Fn cosine theta is equal to mg. Okay? Fn cosine theta is equal to mg. So the normal force is equal to mg divided by cosine theta. Okay, much different than our inclined plane problem from chapter 4. All right, so the normal force is mg over cosine theta. Now what is contributing to the centripetal acceleration? It's the normal force in the r direction. So I set the normal force in the r direction equal to ma centripetal. The normal force in the r direction is Fn sine theta. So Fn sine theta is mv squared over r. Now what I do is now I solve this for the normal force. Normal force, normal force. Maybe you know the mass of the car, maybe you know theta, you could calculate it, that's fine. I'm not going to do that. I've got two equivalent expressions right here. Both of these expressions right here are equivalent to the normal force. So I'm going to set these two equal to each other. Right? So set mg over cosine theta equal to mv squared over r sine theta. The masses go away again. And let's get an expression for velocity. Multiply both sides by r sine theta. Right? Multiply both sides by r sine theta, get v squared by itself. So I've got r sine theta g in the numerator and cosine theta in the denominator. Sine theta over cosine theta is tangent theta, so I'm going to rewrite that as the tangent function. Now I can take the square root of both sides, and the max velocity is the square root of rg tangent theta. Right. What's the tangent of 0? Tangent of 0 is 0. Right? Tangent of 0 is 0. Because it's sine theta over cosine theta, right? So if that was 0, we wouldn't have a banked curve at all, right? So this wouldn't hold, okay? So the radius, again, just like with the level curve, the radius has to be larger for the velocity to be larger, okay? All right, so there's my expression, max velocity of a banked curve without friction, right? So let's try one. We've got a vehicle going around a 30-degree banked curve. The radius is 300 meters. If you ever see like a NASCAR track, they're anywhere from a mile long to 2 miles long. The mile-long tracks, they call them short tracks. They got a 1.5 2 mile long tracks. So you can picture one of those banked curves having a very, very large radius, right? If you were sitting in the center of the track, if you were sitting in the pits, you see that the cars are very, very far away because the radius is very, very high. So we've got the angle of the bank, right? It's 30-degree banked curve. It's got a radius. We're going to neglect friction, so we want to know what the speed has to be for the car to negotiate the curve. Okay. And so you're just going to plug those numbers in. I think I missed the calculation there, but so just plug those numbers in. I'll get a solution up. We plug 300 meters in for r, plug 30 degrees in for theta, and then calculate our max velocity. You should get a pretty high velocity, right? Notice I didn't mention the mass here, right? Because the mass of the car isn't relevant. Okay, mass of the car doesn't have an effect on the velocity. All right, so I'm going to do one last problem. I call this the clacker. Back in the day, there was this toy, right? It was like a rod. It was like a plastic rod, and there was these two strings that came off the rod, and there was a metal ball, right, or a plastic ball or something. Then on the other side, you have the same thing. You have these two strings connected to a ball, and you basically just like swung the rod back and forth, and the balls hit each other, you know, on opposite sides of the rod, and it made this clacking noise, right? So I call it the clacker. But this is just one ball, right? It's kind of like a tetherball system type of thing, right? So this is rotating in a horizontal circle, right? So it's rotating around this rod. So all the tensions, right? The tension here and the tension here are equal. They're two different strings, or two different wires, but the tension is the same. So we want to find those tensions and the speed of the object, right? So how fast is it going, and what are the tensions in the string? So I'm going to set up my free body diagram of the object. All right. So I know the mass is 70 kilograms. I don't really know anything else, right? Just what's in the diagram. They don't give me the radius. I'm looking for the velocity. I'm looking for the tension in both of the wires. Now the tensions are the same, so T1 is equal to T2. So what I'll do is later on in the problem, I'll just start calling it T, because T1 and T2 are the same. So I've got gravity, right? I have to account for gravity. There's gravity acting in the negative y direction, and then I've got T1 and T2 acting at these angles. All right. Now T1 is acting at an angle of 30 degrees. How did I figure that out? So I took this line right here, T1, and I made a right triangle with this line, T1, and this 1 meter long section right here. Okay. So this is a right triangle. This is 90 degrees. This is 60 degrees. This angle right here that T1 makes with this dotted line has to be 30 degrees. So T1 is pulling on the object at an angle of 30 degrees above the negative x-axis. Okay. But we're in the r and the z direction, right? So anything towards the center of the circle, I'm going to say is positive. So T1 in the y direction is T1 sine 30. T1 in the r direction is T1 cosine 30. So I've got a y direction vector and an r direction vector. Same thing with T2. How do I find the angle that T2 is acting on the object? They mark this angle right here with 60 degrees. This line right here, I'm going to assume that it's parallel to this line right here. Alright, so this is 60 degrees. This angle right here, this big one right here, is also 60 degrees. That's another pair of alternate interior angles. They're congruent. Okay, so 60, 60. All right. There's probably another way that you could solve it using similar triangles, but I think alternate interior angles is the best way to go here. All right, so T2 is acting on the object at an angle of 60 degrees above the negative x-axis. Resolve that into your x or your r and y components now. T2 in the y direction is T2 sine 60. T2 in the r direction is T2 cosine 60. So now I can write my Newton's second law in this direction, the vertical direction, and then I can write Newton's second law in the r direction. So we're still looking at centripetal motion. Newton's second law in the y direction is the y component of the two tensions in the positive y minus the gravitational force. And that's equal to 0 because they told me in the problem that the object rotates in a horizontal circle. Alright, so it's not going up and down in this direction at all. It's just going around in a circle along this plane right here. Alright, so the net force in the y direction is 0. Substitute my expressions in for T1y and T2y. T1 sine 30 plus T2 sine 60. Add the gravitational force to both sides. So these two tensions, components of the tensions, are equal to mg. Alright, but T1 is equal to T2. So T1 and T2 I'm just going to call T, and I'm going to factor it out from both of these terms. So now I have T times the quantity sine 30 plus sine 60. That's equal to mg. So I'm going to divide both sides by this thing here in parentheses, get T by itself. So T is mg divided by the sine of 30 plus the sine of 60. I can plug everything in. You can use your calculator though. I used to teach high school math, so I got, you know, the unit circle ingrained in my memory here, but you can just calculate that. That's a number we know. Plug the mass in, plug G in, and I get the tension. I get the tension in both cables, 502.2 newtons. Alright, so now I know the tension. That's great. Let's write Newton's second law in the r direction. T1 in the r direction plus T2 in the r direction. Those are the only forces acting towards the center of the object's circular path. T1 in the r direction, T2 in the r direction. Again, there's no centripetal force. There's no magical centripetal force that just appeared. The rotational motion is due to the tension in these two wires. All right. So it's equal to mv squared over r. I'm accelerating in the r direction, right? Because my velocity vector is changing. I've got a centripetal acceleration. So now I can plug everything in here. I think I'm looking for v, right? I'm looking for the speed of the object now. I've got the tensions. That's great. So T1 cosine 30 plus T2 cosine 60, they go in here. Again, T1 is equal to T2, so I can just call it T, factor it out. Now I'm solving for V. Let's solve for V. Let's multiply both sides by R, divide both sides by M, and I get this expression for V squared. So I know cosine 30, I know cosine 60, I know the mass, I know the tension. I'm missing R. I'm missing the radius of the circular path. So how am I going to find that? The radius of the circular path is actually the distance between this object and this rod right here. Okay, so I got to find that length. Now the diagram tells me that this length right here is 1 meter. So I'm going to use this right triangle right here and a little bit of trig to find the length of this side, which is R. So here's the right triangle that I made. Okay, I'm given this length of 1 meter. I know that's 60 degrees. I know that's 30 degrees. I'm looking for that length right there. That's the radius of the object's path. So I'm going to use the tangent function. I think you've got, I think that's the only one you can use because you have the opposite side. You're looking for the adjacent side. That looks like the most straightforward way to find it. So the tangent of 30 is the opposite over the adjacent. So it's 1 meter over R. Solve this for R. Multiply both sides by R, divide both sides by the tangent of 30. R is 1 meter over the tangent of 30, which is 1.73 meters. Okay. Again, that makes sense. If you were a math superstar back in the day, if you weren't, I don't blame you. I wasn't. Okay. But if if you were crazy about math, you probably recognize this special right triangle, right? And you could have said x root 3 2x, right? You could have just multiplied that by root 3. But I use trig. I just used my tangent function because I had the opposite side. I needed the adjacent side. Okay, and it makes sense because the smaller side is across from the smaller angle, right? 1 larger angle 1.73, so that makes sense. So the radius is 1.73 meters. Now I've got my expression for my velocity, and I know all of these quantities, right? I know r, t, and m, plug them in, and I get a velocity of 17 meters per second. Okay, this is no friction, right? So the speed is kind of low for a car. There would be friction between the tires and the surface, so you would be able to go around this turn faster because there would be a component of friction acting towards the center of the circle. But in this case, we neglected it. Okay. All right, so that's chapter 7, rotational kinematics and centripetal acceleration. All right.